Καλησπέρα, Ανδρέα.
Καλησπέρα. Με ακούτε κανονικά?
Εγώ σε ακούω, δεν ξέρω τα παιδιά. Απλώς σε είδα και είπα να πω καλησπέρα.
Καλά. Τι κάνεις, πώς είσαι?
Καλά. Ευχαριστούμε για την ομιλία και για τη βοήθεια και στα θέματα.
Χαίρομαι που μπόρεσα και βοήθησα και συμμετείχα.
Μας χαρά μας είναι. Μπράβο, ναι. Μπράβο στα παιδιά, γιατί τα παιδιά το συντονίσανε και το κάνανε, οπότε εμείς απλώς είμαστε εδώ για την αιγίδα που λέει.
Ναι.
Οπότε μπράβο τους, όντως, είναι δυναμική. Αν και μικρή είναι δυναμική, οπότε ελπίζω αυτή η δυναμικότητα να συνεχίσει και στο μέλλον.
Ναι,
και φυσικά και σε όλα τα παιδιά που συμμετείχαν, γιατί για να έχουν έρθει να συμμετάσχουν και να συμμετάσχουν στο αγωνισμό, σίγουρα θα είναι... Ωραία. Οπότε, κλείνω εγώ, γιατί δεν είναι ο ρόλος μου. Εγώ όπως καλωσόρισα και λόγω για το τμήμα. Έχεις πολύ σχεδόν στον κύριο από το Διονύση του Παπαγιού, αλλά κάτι τον κράτησε μακριά σήμερα. Αυτά.
Ναι. Ωραία.
Ευχαριστώ.
Καλησπέρα σας. Γεια σας κύριε Ζούπα, ευχαριστούμε που είστε μαζί μας. Καλώς ήρθατε όλοι οι θεατές στη τελευταία ομιλία του διημέρου του διαγωνισμού PLANCKS 2021. Οπότε θα θέλαμε να σας παρουσιάσουμε το τελευταίο ομιλητή μας σε σειρά, που είναι ο δόκτωρ Ανδρέα Ζούπας, τον οποίο ευχαριστούμε θερμά που παρευρίσκεται μαζί μας, καθώς και για την συμμετοχή στην υποστήριξη της διοργάνωσης που έχει πραγματοποιήσει όλες αυτές τις ημέρες. Ευχαριστούμε θερμά. Ορισμένα βιογραφικά στοιχεία του κυρίου Ζούπα είναι ότι απέκτησε το 1992 πτυχίο φυσικής από το Εθνικό και Καποδιστριακό Πανεπιστήμιο Αθηνών. Συνέχεια συνέχισε σε μάστερ στο Πανεπιστήμιο του Cambridge. Το 1997 απέκτησε το διδακτορικό του στο Κολέγιο Imperial του Πανεπιστημίου του Λονδίνου, ενώ έχει υπάρξει επιστημονικός ερευνητής στην ομάδα βαρύτητας στο Ινστιτούτο Ενρίκο Φέρμι στο Σικάγο. Σας ευχαριστούμε θερμά που βρίσκεστε σήμερα εδώ μαζί μας. Είναι μεγάλη τιμή για το σύλλογό μας να έχουμε μια ακόμη ομιλία από έναν τόσο σημαντικό ομιλητή, οπότε θα σας δώσουμε το λόγο για την ομιλία σας. Θα υπάρξουν μετά κάποιες ερωτήσεις είτε στη φόρμα είτε μέσα στο Microsoft Teams και σας ευχαριστούμε θερμά που παρευρίσκεστε πάλι μαζί μας.
Εγώ σας ευχαριστώ που με καλέσατε. Ελπίζω να το έχω εκεί. All right. So, can you all see?
Yes.
Yes, okay. So, now?
Yes, I can see the transparencies, Andreas. I see them. Yes.
Okay, all right. This is very nice. Thank you very much. Should I start? Are we ready?
Yes, we are ready.
Okay. So thank you very much for having me here. The title of my talk is Decoherence in Quantum Mechanics. And to be honest, while preparing the talk, I thought that it is better if the subject gave me the step to talk about issues which are related to the foundations of quantum theory, without the stress to present decoherence and the school of decoherence, the school of thought of decoherence, if we wish to call it this way, to the students. So for me, it's really not so important to get into the details of what decoherence really is and how, on a technical level, we can use decoherence to explain, for example, the emergence of classical behavior or to describe or explain what we call the measurement problem in quantum mechanics, as it is to talk about these problems and see what these problems are and what the proposal of the coherence is. And then there is bibliography that I will need to append. I take it for example, since I think I forgot that, but I will do it. So you can start reading, let's say, for yourselves about this approach to quantum theory. So let's start about decoherence. What is decoherence? What we mean when we talk about decoherence? As we know, quantum mechanics is characterized by what we call interference phenomena. The most typical example is the two-slit experiment that we send many electrons through a screen. The screen has two narrow slits, and then we try to detect the electrons on a second screen. And we ask the question about the probability of detecting the electron location on the screen. If we think classically, try to interpret this experiment classically, then our logic would say the following. Sum over the probabilities of detection of the slits multiplied by the probabilities for detection at the screen, conditional on detection at the slits. In other words, we need some conditional probability that what is the probability that I will detect the electron on a part of the screen given that it has passed through slit 1 or through slit 2. Well, this is wrong. The above probabilities, the probabilities I just described, correspond to a completely different experiment. And the experiment is the following. Detect which slit the electron went through each time. And we say it's wrong because if we simply observe the pattern on the screen, then what we will observe is an interference pattern, the same as if I had a wave impinging on the two slits, all right? And I would not have what the classical way of thinking would give me. So, since there are no detection, my quantum theory tells me that the correct expression should contain an additional term, and we call this term interference term. Interference term requires information, let's say, on what happens at both slits. The idea is that if one performs not the idea, a very interesting point is the following, that if one performs the experiment by throwing one electron at a time, and this is something that we can definitely do, then we will observe small dots on the screen each time, but the collective picture, the total picture, after many electrons have impinged on the screen, will be the picture of interference, of an interference phenomenon. So this is the main characteristic of quantum theory. And as we know from elementary wave mechanics, the interference pattern that we observe depends on the relative phases of the two waves. But now, what is decoherence? Decoherence is exactly the suppression of such interference effects. All right? And we observe that in many situations, and the study of such phenomena where interference effects are suppressed is the theory of decoherence. So essentially, it is a mechanism. Sometimes it could be an artificial, for example, result of the formalism of the theory, but in many other times it could be a spontaneous, for example, result and the result of the dynamical evolution of certain systems under conditions. What are the implications of decoherence? The first one is practical. I thought I should start with the practical one. Well, the practical has to do with quantum information processing systems related to quantum computing, which is a very hot subject lately. And the idea is the following, that we do not want decoherence to work, because if decoherence works, then it will destroy exactly what we need in order to have a quantum information processing system to work. So this is one of the main reasons, very practical reasons, for example, for studying the phenomenon of decoherence. The second, which is something that I would need to focus on, is foundational, the second group of implications. It is related to what we call the quantum measurement. It is related to the emergence of classical behavior. Sometimes these two problems are not, it's not easy to distinguish between the one and the other. They are clearly interrelated. And then finally, it has implications about the arrow of time. So a little bit of history about decoherence. The decoherence as an independent subject started during the 70s with the pioneering works of Che. I really do not know how to pronounce the name. It's spelled Z-E-H, all right? And in the early 80s, by contributions of Zurek. And we say that as an independent phenomenon, because suppression phenomena were studied much earlier, and their study dates back to the early days of quantum theory, 1929, by the studies of Mott about the trajectories of particles. Now, I assume that there is a basic knowledge at the level of an undergraduate course of quantum mechanics, in the sense that you are familiar with the notion of wave function, of Hilbert space, of self-adjoint or Hermitian, as we call it, operator. There's a subtle technical distinction, but this will not. This is something that we will not talk about. Not that I will very much need them, but mostly because if someone hears a lot of new terms, then this tends to make it much more difficult to understand what the talk is about. But I have to make that assumption, since I guess most of the audience are students of physics. So assuming this knowledge, I would like to talk to you about an object, which is the density operator. Now, the first contact with a density operator comes when one wishes to study ensembles of quantum systems, what we call a mixed state. What is a mixed state? We denote it by rho, symbolize it by rho. Here, we mean that we have wave functions, D, a number D of wave functions. And then we have some classical probabilities, W1 up to WD, of observing or selecting, put it anyway, each wave function every time. Actually, this is a classical probability that the system is in the state described by the wave function psi d. For example, this is what WD is. Of course, the WD numbers, given that we have the interpretation of probability, they should all be less than or equal to 0, not strictly greater than 0, greater than or equal to 0 and less than or equal to 1, and there is some should be equal to 1. Now, the reason why one would want to do that is, first, there are quantum states that need to be described by such an ensemble of system, and there is a very typical quantum state, a thermal state. When one works on quantum statistical mechanics that needs to use the notion of density operator. But apart that, even if one wants to prepare a system, well, I have not talked to you about state preparation yet, but this is something we will do very soon. We cannot prepare a system in a state with an exact, for example, value of certain observables. So we will result more or less in states which are not actually the same, and we have to take into account the classical probabilities of obtaining, for example, one state or the other, much the same as when we work on, for example, the experiment in the physics lab, undergraduate physics lab, and we measure the time it takes for some object, for example, to cover some distance. We do not get the same result every time we repeat the experiment, we run the experiment. So think of it as in the same way. Then we define the mixed state operator, which is the sum of these projection operators. I assume familiarity with projection operator. It essentially describes what the parenthesis above gives us, that it is the most general description of a system, and it takes into account, for example, the fact that we might have states with different probabilities. One thing to notice here is that these wave functions psi d do not have to be orthogonal. Okay, this is something which is very important. So when one describes the system by using a density operator, the question is the following: what is, for example, the probability of having an observable taking on a value an that we know it is identified with an eigenvalue of the self-adjoint operator representing the observable in the given state rho. This is given by the trace of the corresponding projection operator, the projection operator that projects onto the eigenspace that corresponds to the eigenvalue an. And then, if we need the expected value, the average of the density operator of the observable, then this is given again by the trace of rho times the self-adjoint operator that represents in quantum mechanics on the Hilbert space the observable A. These are the two basic notions. These are generalizations of the respective notions one is acquainted with when is taught an introductory course in quantum theory. So we generalize, and any operator with the properties, first, that it is self-adjoint. As I said again, I will not get into technical detail, with semi-definite, as we call it, which means that its average is always greater than or equal to 0. In other words, its eigenvalues as well are greater than or positive, and whose trace is equal to 1 is called a density matrix or a density operators. And it might seem as if what I just did earlier is a generalization of the quantum mechanics you were taught at an introductory course. And the question that we could ask is the following: can there be another such generalization? Can we find another object that would assign probabilities, for example, to states of quantum systems? Well, the answer to this question is no. Density operators provide the most general description for the state of quantum system. This is known as Gleason's theorem, and it results from a set of very basic and elementary assumptions. Not that the theorem itself is basic and elementary, but the assumptions that it makes are really basic, elementary, and very general. So this is the most general description. If we now have a density operator, since at the end we would like to talk about decoherence, which is related to the absence of interferences, we need to say that quantum interference is expressed exactly by the off-diagonal elements of the density matrix. And this is something very dangerous. Not that this happens, but what is dangerous is that the conclusion we might try to draw out of it, and this is why I have a question mark, that diagonal density matrices express true classical ignorance in the sense that they express true classical probabilities, objective ignorance in the sense that it is lack of knowledge that makes us assign probabilities to the system and nothing else, and that the diagonal elements are classical probabilities. Of course, this system, this problem, and this question is very complex, but one aspect of it, which is related to what I'm going to talk about now, gives the following answer. No, your conclusion or my conclusion is wrong. And why is it wrong? And the next question that one would like to ask is the following. Is this mixed state decomposition unique? When I say mixed state one, well, unfortunately, I have to go back a bit. The decomposition that mixed state operator gave you, this is the decomposition I'm referring to, which, according to what I said earlier, is there to reflect some classical probabilities when we study quantum systems. And it turns out that this decomposition is not unique. Density operators do not admit a unique decomposition of the type of equation 1. Well, what is the resulting problem? There is not a simple interpretation of the density matrix as a measure of our ignorance of which pure states should be used to describe the system. And since this sounds very general, what I am going to do is I'm going to present you with an example that exemplifies exactly this. Suppose that you have a spin half system. Then I take the matrices that describe the projection of the spin along the z-axis. So the first one is spin up, it corresponds to spin up. The second one corresponds to spin down. And then at the second row, I have the two operators that describe the spin along the x-axis. Call it left and right, whatever you like. But it's, again, the same. So we have these two sets of spins up and down along the z-axis for possible states of spins, and left and right along the x-axis. Now take the following density operator. This is a diagonal density operator. It is very easy. It is an exercise of elementary linear algebra to see that this density operator decomposes in the sense that it can be written as a linear combination of either the two spin 1/2 matrices along the z-axis, or either the two spin 1/2 matrices along the x-axis. So if we measure the spin, we cannot simply identify the original picture. We have no idea, all right, what the spin originally was, since we have the same probabilities for obtaining spin 1/2 along its axis on either direction. So this is what I meant, that the density operator cannot be used to represent the lack of knowledge about some, let's say, objective property that the system had before measurement. Now, another very important property of a density operator is that the set of density operators, this is a rather technical term, would not really need to go into details, is convex. It means that this affine sum, as we call it, well, it is called affine because the coefficients are I, are numbers which are positive, and they sum to 1. Well, any such combination is again a density matrix. The only density matrices that cannot be decomposed into an affine sum are ones of the following form, of the form of projection operator on the subspace spanned by state psi. So this is called a pure state. So the wave function, in a sense, all right, is called a pure state. The rest of states are called mixed in quantum mechanics, and mixed now, not in the classical meaning of the word mixed, because they are not pure according to the above definition. What is the time evolution of a density operator? Well, under the assumption that the time evolution preserves this linearity or the affine structure of the space of density operators, then the linear evolution of the density operator is given by the commutator of the density operator with the Hamiltonian. But there are two things that I would like to point out, and which are very important, and actually they are the main reason that I give you this formula in relation to the notion of decoherence. We will come back to this at the end of the talk. Now, evolution under the above law can never take a pure initial state into a mixed later state. Cannot produce that. And of course, it is a deterministic equation. We can specify the initial state psi 0, which means psi at time 0, and the theory predicts the state. This is a typo here, of course. I mean that I should have a key at a later time. I will have to correct it. Now that I have completed this kind of background into what the most general description of a quantum system could be, I would like to talk about the feature of quantum theory that we have to deal from now on. And this is dynamical evolution versus measurement, as I call it. Well, Schrödinger equation is deterministic. If I know, as I used later, if I know the state at an earlier time, then I can predict 100% what the state would be at a later time. And it is also a linear differential equation, which means that any linear combination of solutions is again solutions, and that leads to the superposition principle. Now, assuming that in the introductory course to quantum mechanics, you have at least heard about quantum measurement, measurement is nothing like that. It is probabilistic in nature. This is possibly what we've been told, that for example, what we have a self-adjoint operator, and then we have probabilities of measuring, for example, eigenvalues of this adjoint operator whenever an experiment is performed. So that's what we mean when we say it's probabilistic in nature. We cannot make definite predictions about measurement outcomes. The theory only assign probabilities to the various alternatives, which is, as I said earlier, for example, for a given observable presented by self-adjoint operator, the alternatives are the different, for example, values that the observable can take, the eigenvalues of the self-adjoint operator. So we have a problem, a measurement problem. I will use this term many times, all right? There seems to be a fundamental distinction between dynamical evolution and the act of measurement. And this is something that creates an uneasiness with the way we understand quantum theory. Having said that, since we talk about the measurement problem, quantum theory is one of the most successful theories we've made. There hasn't been an experimental test that quantum theory has not passed. Whenever it has been tested, it came out that it said the truth. Quartz said the truth. So this is the peculiar thing about quantum mechanics, even though so far it has passed every test, let's put it this way, still we feel very uneasy with the way we understand quantum mechanics. And this is something that one has to, for example, make very clear. And of course, my position, that we feel very easy with what quantum mechanics really says, is just a personal opinion, because there are many physicists who think the opposite. Okay. Now, what are the essential features of the measurement problem of quantum theory? Well, it seems that there is an intrinsic randomness of measuring processes. There is a breakdown of linearity. It is related to what you probably heard as a collapse postulate. And, of course, why should the measuring process be governed by physical laws than other process that, let's say, quantum theory describes? So the measurement problem is not just one problem. I'm not referring to all in the sense that it is a group of problems. It is a complex of problems. And of course, there is not a universally accepted formulation of what the measurement problem really is. So what are the phenomenological features of quantum measurements if we wish to understand better what the measurement is? Well, measurements have results. We get a definite outcome every time we perform the measurements. Results are obtained with certain characteristic probabilities. And then after the measurement, the system is transformed in a characteristic way. Let's say that this is related to the reduction postulate I talked to you about in the previous slide. So these are the three phenomenological features of quantum measurement. Now, I would like to give you some background on the measurement problem. This is what I'm doing from the very beginning, trying to build the background in order to understand what the measurement problem is. And the very important ingredient of what the measurement problem is the meaning of the wave function. So there are roughly two major schools of thought. The major difference being, and this is not exhaustive, this is not the only difference, but it lies at the heart of the different positions they stand for, all right, is the way that the quantum system, the state of a quantum system, is interpreted. The description I'm going to give you below is neither exhaustive nor exclusive. Okay, so this is a very rough description, but The basic idea is the following. First, the first school of thought, that the state should not be associated with an individual system. This might sound as a surprise to most of you. It only refers to an ensemble of copies of the system. And what we do on these copies, we perform repeated measurements. And the state simply quantifies our knowledge of the system. So there is not any kind of physical attributes given to the wave function. It's simply a calculational tool. Let's put it this way. This, let's call it the anti-realist position, school of thought. And then there's a second school of thought that the state refers to the individual system itself. Individual systems possess value for all the physical quantities, and we make that clear. Quantum theory predicts probabilistic distribution of possessed values, and this is not just a theory of results of measurement. And of course, that measurement is not fundamental. Okay? And quantum theoretical probabilities are a reflection of our lack of knowledge of what is actually the case. Not necessarily all of these are agreed upon by people who belong to what we call the realist school of thought. But these are the two main differences. You could also have people who get a mixture, for example, of attributes of one or the two schools. So this is a very, 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 I repeat that, rough description. Now, to sum up what the conceptual issues are when it comes to the measurement problem, let's first say that the measurement problem is mostly, or the questions related to the measurement problem are mostly raised by attempts to have states or properties or both posited by individual systems. All right. So those are mostly questions raised by people who belong to what we call the realist school of thought. And the conceptual issues are the following. First, the meaning of probability. Second, the role of measurement. Third, the reduction of the state vector. And fourth, quantum entanglement. They're put in a very, let's say, random order, not in, for example, in an order of increasing significance. Now, I will not talk very much about the meaning of probability. What I would like to say here, though, is the following, that we need to understand the difference between probabilities in classical, for example, physics, and probabilities in quantum mechanics. Since we know that quantum mechanics is a probabilistic theory in the sense that the most accurate knowledge that we can have of the system is the wave function, and the wave function, the only thing that it does is to give probabilities. And I would like to focus on the rest three of the issues in what follows. Now, in order to understand what really happens, we need to talk about the reduction of the state vector, and it is essential that we distinguish with what we call state preparation and what we call measurement. If we need to make or repeat a number of or run a number of measurements of experiments on a system, we have to make sure that the individual systems that we measure are identical, so that they are all in the same state. Measurement and state preparation are different, all right? What state, actually, I will say the following. I should have started with state preparation, even though I present it like that. A measurement frequently destroys the system, while state preparation causes the system to be in a particular state immediately after. All right? So state preparation prepares the system, and then we measure it. Roughly, what state preparation does for an observable is the following. It produces a collection of systems, the state of which is guaranteed to be an eigenvector of, for example, the observable we wish to measure, of the self-adjoint operator A, which represents the observable. Let's say that we throw in some electrons with spin along random directions. We pass them through a magnetic field. The magnetic field is along the Z axis. And state preparation is the fact that we force, for example, the spins to either align up or down. This is a state preparation. And then, once we have done that, we perform the measurements on the system and check whether the probabilities that we measure agree with the ones predicted by our theory. This is essentially what state preparation is about. Now, once we have prepared the system, there are two options that we have. Either to select a sub-collection corresponding to a particular eigenvalue, which means in this case that we have a reduction of the state vector from the state psi to the eigenvector corresponding to the eigenvalue am. And this is what in the relative frequency interpretation of probability, this transition is called reduction of the state vector. And this is usually presented as a postulate. You've probably heard of it. It is the well-known von Neumann's projection postulate. And it is something that cannot be derived from the existing formalism. We take for granted that this is what happened. There is not a mechanism to explain why and how this happens. All right? Now, again, within the relative frequency interpretation of quantum mechanics, we made sure after state preparation to keep the whole collection. Well, as I said earlier, giving you the example of the spin and the electrons passing through the magnetic field, what we have done, we have somehow divided the ensemble that we have into subsystems, each corresponding to a given eigenvalue. This is what the EM subsystem represents. For example, in the case of electrons, we have two subsystems, one collection with the electrons having spin pointing up, and the other subsystem having electrons pointing spin down. Then the correct description is the next state, which is given by the sum over all the modulus of the coefficient. If we expand the state psi into the basis of the eigenvectors of the self-adjoint operator, and this is one of the many and great uses of adjoint operators, that they give a full basis that allows us to do that. And this modulus squared is nothing else but the probability that of finding an individual system into the state AM. Why that? Because this expresses the fraction of systems that lie in the subsystem EM before the measurement is made. Well, the thing to point here, and the thing that one has to be very careful about, is that there is a double role played by these coefficients, these probabilities, let's call it. One, before measurement, the coefficients in the mixed state represent quantum probabilities, but after the measurement, they are to be interpreted as classical probabilities. They simply do the express ignorance about the system vector state. We have no idea after, for example, the electrons have passed through the magnetic field. We know that some electrons have spin pointing up, some other electrons have spin pointing down. We know that this happens with a certain probability, but we have no idea if we decide not to perform the selective measurement what the state really is. Again, the term state reduction is also used to describe this tradition, going from the pure state to the mixed state. And here comes the realist view, the question of the realist. Well, state reduction, the term state reduction, is also used by those who associate the state with a single system. What is the assumption that we make? That, well, a single measurement on the system will cause a reduction of the state vector, but this reduction has nothing got to do with system selection. It is a physical reduction. The system suffers something, okay? Something real happens to the wave function. The overall time development is described by the following picture. We have sharp jumps produced by the act of measurement, and these are separated by periods of deterministic, in other words, Schrödinger equation. So this is what happens. And now the issue is the following. What is the nature of these jumps? All right? Can we obtain them from the existing formalism? And this is a very important question. One has to ask if one, of course, takes this stand. Or the other thing that we have to do is to add the reduction of the state vector as a fundamental postulate. Why that? Because we have assumed that measurement is not fundamental. So if for us measurement is not fundamental, then we have either one of the options. And the natural question, what is it that really happens? Well, in this framework, the reduction of the state vector then is related, is expressed as an uncontrollable disturbance of the system. And the question is the following. Since we have an uncontrollable disturbance, what kind of interaction serves as an unideal measurement? Is state reduction the outcome, for example, of dynamical evolution with both observable and apparatus regarded as quantum mechanical systems? This is a question. If, for example, we take it for granted that quantum mechanics is a complete theory that describes everything. And if we can do that, or independently of whether we can do that, what kind of interaction between two systems is to be regarded as a measurement of one by the other? All right? Again, these two questions are interrelated and very important questions. Excuse me for a moment because I really have... okay. All right. So I'm worried a little bit about the time, but I think it's okay. Now we come to that. We have posed this question as well. We come to quantum entanglement. This is the heart of quantum theory. And if you ask me, my personal opinion is even if all other features of quantum theory vanish or need to be changed, I believe that quantum entanglement is here to stay. But this is my personal opinion, and I have no, and there is, since it is an opinion, no way of, for example, establishing it as a scientific fact, if it even makes sense to talk about it. And actually, the first one to really understand what the role of quantum entanglement was Schrödinger himself. All right. Now, what is the idea? The idea is that since, for example, we have two systems, system 1 and system 2, we need to describe them in the tensor product of the corresponding Hilbert spaces. But the most general state in this tensor product is not of the form of a product state, as we have here, but the most general state is of this form, where we have the state, for example, the basis corresponding to system 1 and the basis corresponding to system 2. So the state cannot be associated with vector states of the subsystems S1 and S2. The state is a linear superposition of independent states of each of the systems. They interact and they become entangled. This is the main idea. For example, let's take measurement of spin. Let's suppose that we measure SZ, which is the projection to the third component spin. Let's call it like that, of an electron along the Z axis. Then we know that the eigenvalues are h bar over 2 and minus h bar over 2. And the relevant eigenstates are the up and down eigenstates. Suppose now that we wish to describe the measuring device by quantum mechanics. Then we define three apparatus observables. A0, which corresponds to the resting position, let's say the pointer of the apparatus. The resting position corresponds to an eigenstate A0 of the observable. Then we have the position up, which is measurement of spin in the up direction, and it corresponds to an eigenstate A up, let's call it. And then, of course, a measurement of spin down, which corresponds to an eigenstate A of spin down. Now the example continues. Suppose that the initial state of the two systems is a product state where spin up is correlated with A0 state. Now, because of the interaction of the system with the apparatus, the state will evolve to other correlation of the up state of the spin with the up state of the pointer. And like that, we do know that we have a spin in the up direction because we read the value of A. Similarly, if we have a spin down initial state that interacts with the measuring device, then after measurement, this will evolve to product state. And of course, we will understand by reading the pointed value along the down direction that the spin was indeed the spin down state that we had initially. But now, suppose that the electron does not start in a given eigenstate of the spin operator, but assume that it starts in a linear superposition of states. For example, a state up and state down. Obviously, we have the probabilities, the coefficients have to sum to 1, but then linearity of the Schrödinger equation implies the following, that since A0 interact with the up and down, for example, in states of the spin, then this will give us a linear superposition of the product state of spin ups and the product state of spin downs. When I say product state, I mean the product state of the pointer and the spin of the particle, and the product of the state, again, of the pointer and the spin particle along the down direction. It does not correspond to either the atom or the apparatus being associated with any specific state. Like this, we have no idea what the outcome of the experiment is. No state reduction has taken place, and we have both possible outcomes of the measurement problems having an equal status. I'm not talking about equal probabilities, equal status. So the conclusion is the following, that even if a composite system starts with an initial state where each of its subsystems is meaningfully associated with the state, the time evolution is such that after and because of the interaction is very important. You have to have interaction in order to have the system to get entangled. The state will typically be a linear superposition of product states. And the question is this acceptable? Well, why do I ask the question? Because one of the composite systems is macroscopic. And I cannot have superposition of macroscopic states. Recall Schrödinger's cat. All right. Can a macroscopic system exist? Superposition of the collective observables that describe its macroscopic properties. Well, here there are some mistakes, spelling mistakes, but okay, especially with the but I will have to correct them as well. But this is the main question that we have to ask. So let's specialize a little bit more on the measurement problem. We saw how issues presented so far are correlated in one way or another to the role of measurement in the theory. They all contribute to what we call the measurement problem, each of them in its own way, to a greater or to a lesser degree. And we now wish to answer the following question. We focus on the issues which are related to decoherence. We try to make our question more technical in a sense. And the question we are asking related to the measurement problem is the following. How the entangled Schrödinger time evolution of objects plus the measuring device can be reconciled with a picture of the reduction of the state vector? Since this is what we observe. What breaks down the linearity of the Schrödinger equation, all right, and the predictability of the Schrödinger equation? I would like to focus on the measurement problem when we have no selection, when we decide not to select the outcomes. So from the entangled vector space, as it is the one that we resulted with earlier, after making an ideal spin measurement with no selection of results, we obtain a density matrix, which is a mixture. All right. And then see what really happens. We start with a vector in the Hilbert space of the composite system, because we have the Hilbert space of the apparatus and the Hilbert space of the system. Remember that we suppose that both are described quantum mechanically. We suppose and we assume that quantum mechanics is universal. It describes everything. All right? Because the measuring device, if someone would like to think about it, consists of atoms. Atoms, for example, are described by quantum mechanics. Why should a large collection, for example, of atoms making up the measuring device not be described by quantum mechanics? And then we result with the mixed state in the hyperspace of the electron. What the second equation tells us is that if we perform the measurements at the fraction expressed by the modulus of a squared of cases, we will observe spin up, and at the fraction expressed by the modulus of p squared, we will get the spin down. These are the two probabilities, in other words. Now, what is the obstacle in this case? Because if we like to think of it as being the result of some dynamical kind of evolution, then remember, what is it that we pointed out when we talked about the time evolution of the density operator? That the mixed state cannot in any way be derived from the entangled vector. No way. Oops. Sorry. Yes. Now, I mean, I thought I had a mistake. I'm sorry about that. I got confused. So, to repeat the question and make it clear, if the mixed state is to be derived from the entangled vector in some way, not any way, not in a relative frequency, for example, way, or simply continuation way, but as the result of a physical interaction, we cannot have that with Schrödinger's equation. It never leads a pure state to a non-trivial mixed one. This is the main idea. So what do we do about it? Now, what is a possible conventional resolution? I will not talk about all the possible answers that one could give or interpretation or school of thought about this problem. Well, one way to think about it is that there is no real problem, because at the end, what we do is we only wish to study a physical quantity B for the electron and nothing else. All right? And if we do that, then the predictions of the two states do not differ. What do we mean by that? What we mean by that is the following: that we will throw away, quotes, throw away, the Hilbert space of the other system, the system which is not of interest, let's call it measuring device, now, and thus the observable B is to be presented by this operator, which is the tensor product of two operators. The operator one, the identity operator acting on the Hilbert space of the other body, be it the measuring device or any other particle with which, for example, the electron interacts. And hence, in this case, we try to measure the average or the expected value of the observable B in the entangled state by using the specific operator. Then this will give exactly the mixed state we expected. All right. Now, what is the meaning of what we do? Because it might sound a bit strange. Well, essentially, what we do is we trace out over the degrees of variables of a measuring device. This is what we do in this case. That's what this operation means. We're not interested at all, but we somehow take it's, well, I don't think this is the correct term to use. It's collective, for example, effect on the system. Even though I'm not quite sure that this is, you should take this for granted. Now, what we result with when we do that? When we do that, we result with what we call the reduced state of the system if we ignore the degrees of freedom of the measuring device. The nice thing now is that when the state of a composite system is in an entangled state, then the reduced states of the subsystems are mixed states. So at least on a technical level, like that, we solved the problem that was posed by the Schrödinger evolution. But one has to be very careful about it, because on the one hand, probabilistic predictions between the two states are equal, but only for quantities that pertain to the electron alone. Physical quantities involving both electron and apparatus will reveal differences between the two states. Now, the fact that they reveal differences between the states mean that there is interference. Because that's what interference does. So this is not a proper mixture. A proper mixture is a mixture in the classical sense. It only reflects classical probabilities. So that's the reason that such mixed states are usually called improper mixtures. Related to the problem I posed earlier and to the attempt to answer some of the questions posed is the notion of relative state in attempts to solve the, for example, measurement problem. Now, the relative state is a notion which is related to the what is called many worlds interpretation of quantum mechanics, and it originates in Everett. I'm pretty sure that you've probably heard of the many worlds interpretation, sometimes used correctly, sometimes abused, but the main idea is the idea of the relative state, and it is the following. Suppose that you have a system in a compound state. Then, if we trace out over the degrees of freedom of the state 3, 5 in this case, what we get is a state of system 2 relative to the state xi of system 1. Now, the problem is the following, that this decomposition is not unique. And again, one may present you with an example that takes a spin state of 2 electrons, of a composite system of 2 electrons with total spin equal to 0, and one can show that this decomposition is not unique. So in a sense, we cannot use this to say that by tracing out what we get, even if we neglect the problems posed by the fact that we do not take into account the second system, even if we do that, how can there be an objective description of the system when the decomposition is not unique? And this raises the problem of what we call pointer basis in quantum theory. A pointer basis is a special basis set for the Hilbert space, and it is needed because this is the basis with respect to which we want to uniquely describe the system. One of the attempts to find such a basis involves the interaction with the environment and the mechanism of decoherence. What is the basic picture now? Well, I have to say a few words. Decoherence actually became very attractive within quantum cosmologies and has been advocated by quantum cosmology. Well, the idea was the following, that if one works on quantum cosmology, one wants the universe to be described by quantum mechanics. And if one wants the universe to be described by quantum mechanics, in other words, quantum mechanics to be a universal theory, then you cannot have a distinction between measuring devices and quantum systems. And if the universe is to have properties, let's put it this way, how do we attribute these properties to the universe? So many of the people who worked on the field of quantum cosmology initiated the program of decoherence, and actually not only them, but a couple of them are the people who founded the field of decoherence in modern times. Because remember, as I said, that decoherence as an independent field goes back to the 70s. So the first is that it became very attractive. Now, why that? Because the earlier works on decoherence had shown that macroscopic objects are usually strongly correlated with their environments. These are the works of the early 70s, for example, and 80s. So, in this sense, decoherence induced by the environment, in the sense decoherence which resulted, which is a consequence of the interaction of the system that with an environment where, well, an environment is taken to be another system that has many more degrees of freedom, and this is the main idea. For example, the air around us, all right, seemed to be the original machinery to use to show why we do not observe macroscopic systems in superpositions of macroscopically distinct states. So we have the mechanism. And this is what I was referring to when I said that decoherence is the theory of the suppression or the absence, let's put it this way, of interference. The state of the system may decay into a mixture in a basis determined both by self-dynamics of the system, HS, that's what it means. H is supposed to be the Hamiltonian of the system, and the Hamiltonian that has to do with the interaction with the environment that we call it HI. Well, the environment absorbs the relative phases and hence delocalizes them and results in correlation with the system. Well, now, contrary to what, for example, one would possibly expect, we have very strong correlations between the system and the environment in order to have decoherence. Even though it suppresses interferences, this suppression of interferences is a result of the very strong correlation of the system with the environment. Well, in the system studied so far, decoherence has proved to be very effective. For example, there are durations of the order of 10 to the minus 12. Well, I might be very optimistic with that. I remember that when I was first working on the field of decoherence, the estimates were of the order of 10 to the minus 24, but I expect that they were very over-optimistic. Nanoseconds, I believe, could be a very well estimate for this for the scale of the decoherence phenomenon to take place. So, since the interaction of a system with the environment is unavoidable, one comes to study what we call open systems. So, if the total system, which is the system, plus the environment is described by a density operator that we call it rho total, then the state rho of the subsystem is obtained by tracing it over the environment. When I say tracing it over, I mean tracing the total density operator. Okay. Now, the resulting equation for the density matrix of the system is called master equation. Density operator, evolving according to a master equation, have been the subject of a number of studies concerned with decoherence and the emergence of classical behavior. What is the main idea? Well, the main idea is, that we should have a diagonalization of the system's density matrix in the basis of the eigenstates of the observable O, unknown observable, which satisfies the following condition. That it's commutator with the total Hamiltonian, the system Hamiltonian plus the interaction Hamiltonian equals 0. And this would indicate that difference between the states in that basis is destroyed. So one then would have the right to regard the dynamical variables corresponding to these diagonalization bases as definite. Now, as you probably all know, the interaction Hamiltonian, sometimes expressed by the form of a potential or the interaction stem, are almost certainly, or let's say most of the times, dependent on position. So in this respect, the position variable plays a very special role in decoherence, exactly because of the universal dependence on the interaction Hamiltonian, the interaction between the system and the environment on position. Another consequence of this is that decoherence is approximate. What do I mean by that? Well, the Hamiltonian of the system, if you think about it, contains momentum. It's the kinetic energy. All right? So you almost certainly have a term, the Hamiltonian term, involving both momentum and position. And it is very hard to find a non-trivial observable that would commute with both of them. And this is why we say that we expect decoherence to be approximate. This is one way of viewing this, that such a thing should happen. Actually, this is the end of my talk, and what I would like to say is that what I just presented is just one direction that people that work on decoherence take, which is the environmentally induced direction, decoherence. And there is the decoherence history, as it is called, field. The decoherence history field is more general than the field I just presented, but it includes it. It's not something different. It just tries to understand the role of decoherence as a general phenomenon, as the basic principle that explains the emergence of classical behavior. And as such, it applies not only to closed systems, to open systems, but it applies to to closed systems as well. After all, since the program of decoherence has been advocated by quantum cosmologists, you cannot think of the universe, for example, as being an open system. You have to have a formalism which treats it as a quantum system, and you have to find why and how and under what conditions certain observables will decohere and will be the classical observables of our world. There are many issues related to this approach, and what I would like to close my talk with is the following. The mechanism of decoherence, as I presented it, is interpretationally neutral. It does not belong to either one or the other of or third, let's say, school of thought regarding the meaning of quantum mechanics. It is a phenomenon. What brings interpretational issues into the game is the way we use decoherence in the question we try to ask by using the given mechanism. This is all. Thank you very much. Should I, well, okay, I have finished.
Thank you very much, Professor Zoupas. We will give some minutes to the participants to make to form questions if they have, or they can actually direct ask them here if they feel free to do it.
So all the participants can scan the QR code here in the screen and make some questions through the form, and then we will read them to Dr. Zoupas. For the next 5 minutes, we will wait your questions, and then we will proceed on the results of the science trivia through our secretary, Eva Thermou.
Yes, Mr. Liberos?
Yes, Liberis has a question.
Okay, yes, I would be happy to. I will happy to hear it, and more happy if I will be able to answer it.
Μήπως υπάρχει κάποιο θέμα στη σύνδεση του κύριου Γιώργου Λιμπέρη? Υπάρχει ένα raise hand.
Ναι.
Hello, can you hear me?
Hello? Yes, yes.
My question is about black hole physics. We know that through Hawking radiation, a pure state can transform in a mixed state. What can decoherence say about that?
Well, this is again is not so much related to decoherence, this issue. Of course, it is related to the information paradox, but the whole idea is that Hawking radiation is not so much related to the mechanism I just described, but it is related to the fact that you have a horizon, let's say. And this is the black hole horizon, and that's what actually makes the transition from a pure state to a mixed state. In a sense, if you think about it, you have no access to the information inside the black hole, and that's what the Hawking radiation is about. Another phenomenon which is very much related, for example, to Hawking radiation is the Unruh effect, in which you might have a field and an observer who's accelerating observer will observe that free field, for example, let's take it being in a thermal state, and a thermal state is a mixed state. So this is a very delicate issue, and it is related to the existence in both cases of what we call horizons, the event horizon, first case, roughly speaking, and the Rindler horizon, the second case. I don't know whether I answered your question.
Yes, I'm fine.
Κύριε Ζούπα, σας ευχαριστούμε πάρα πολύ. Δεν είχαμε κάποια άλλη ερώτηση, οπότε ήταν εξαιρετική τιμή που παρουσιάσατε την ομιλία σας σήμερα. Ήταν εξαιρετικά ενδιαφέρουσα. Σας ευχαριστούμε πάρα πολύ εκ μέρους όλου του Φοιτητικού Συλλόγου και των οργανωτών του PLANCKS 2021. Σας ευχόμαστε καλή συνέχεια. Ευχαριστούμε και πάλι που ήσασταν μαζί μας.
Ευχαριστώ πολύ.
Και τώρα θα παρουσιάσει η Εύα Θερμού τα αποτελέσματα του Science Trivia από χθες για τις ομάδες που ήταν στο quiz. Οπότε δίνουμε το λόγο στην Εύα Θερμού.
Καλησπέρα και από μένα. Για λόγους συντομίας θα παρουσιάσω από το leaderboard του Science Quiz, τους τρεις πρώτους. Είναι η Ευφροσύνη Ζάχου με 390 πόντους. Στη δεύτερη θέση έχουμε μια ισοψηφία βαθμών με τον Λιώδη Ιωάννη και τον Μιχαηλάγγελο Πιεράτο να έχουν 340 βαθμούς. Και στην τρίτη θέση έχουμε πάλι μια ισοψηφία βαθμών, τον Λουλούδη Νικόλαο και τον Αλέξανδρο Μιλωνά με 330 πόντους. Και επειδή μερικές από τις απαντήσεις σας μας διασκέδασαν ιδιαίτερα, μας έκαναν να γελάσουμε, δύο άτομα κατάφεραν να ενταχθούν στη λίστα των Honorable Points, που είναι ο Ανδρέας Νάουμαν Θάμπετ με 130 Honorable Points και ο Μιχαηλάγγελος Πιεράτος με συν 20. Αυτά από μένα. Επίσης, ξέχασα να αναφέρω ότι θα ανέβει ολόκληρο το leaderboard στο Discord, όπως αναφέρθηκε χθες.
Εκ μέρους του Φοιτητικού Συλλόγου Τμήματος Φυσικής του Πανεπιστημίου Θεσσαλίας, θα θέλαμε να σας ευχαριστήσουμε που παρακολουθήσατε το διήμερο των εκδηλώσεων. Θα θέλαμε να ευχαριστήσουμε ιδιαίτερα τις ομάδες που διαγωνίστηκαν και τους συμμετέχοντες από όλα τα τμήματα φυσικής. Με ιδιαίτερη μνήμα θα θέλαμε να δώσουμε στην υποστήριξη που είχαμε από την ομάδα PATH του Αριστοτελείου Πανεπιστημίου Θεσσαλονίκης, στους οποίους ευχαριστούμε θερμά και τους ευχόμαστε τα καλύτερα στο πολύ σπουδαίο έργο που κάνουν στη προώθηση της επιστήμης φυσικής στους νέους φοιτητές. Θα θέλαμε να να ευχαριστήσουμε τους χορηγούς μας και ειδικότερα τον Οργανισμό Πολιτιστικής Ανάπτυξης Περιφέρειας Στερεάς Ελλάδας, τις εκδόσεις Κλειδάριθμος καθώς και την Κάνον. Και ταυτόχρονα θα θέλαμε να ευχαριστήσουμε ιδιαίτερα για τις ενέργειές του τον Αντιπεριφερειάρχη κύριο Ηλία Κυρμανίδη, ο οποίος αποτέλεσε αρρωγό για την υποστήριξη μιας τέτοιας εκδήλωσης για πρώτη φορά στη χώρα μας. Εν κατακλείδη θα θέλαμε να αναφέρουμε τους συντελεστές αυτής της εκδήλωσης, που είναι το Διοικητικό Συμβούλιο του Φοιτητικού Συλλόγου ως συντονιστές και ειδικότερα τον Σταμάτη Σερίφη, που είναι ο αντιπρόεδρος του Συλλόγου και συντονίζει την εκδήλωση από το Βέλγιο, την Εύα Θερμού, που είναι Γενικός Γραμματέας, την οποία την ευχαριστούμε θερμά και για το quiz και για όλη τη συνεισφορά της στην εκδήλωση. Θα θέλαμε να ευχαριστήσουμε εξαιρετικά πολύ τον ειδικό γραμματέα μας, τον Σπύρο Τζάκη, ο οποίος παρευρίσκεται εδώ και υποστήριξε με κάθε τρόπο την εκδήλωση, τον ταμεία μας Νίκο Δόδωρα, η συμβολή του οποίου ήταν καθοριστική, τη Βασιλική Ελένη Κοτρονιά, που μας υποστήριξε συνολικά στο συντονισμό και στην υλοποίηση της εκδήλωσης. Ευχαριστούμε, Βάσο. Και φυσικά θα θέλαμε να ευχαριστήσουμε τον Κώστα Πακόπουλο, ο οποίος πρακτικά ήταν υπεύθυνος για τη μετάδοση και για όλη τη τεχνική υποστήριξη από τα γραφικά έως την αναμετάδοση σήμερα, το οποίο θέλουμε να ευχαριστήσουμε θερμά. Κώστα, σε ευχαριστούμε που αφιέρεσες τόσο πολύ χρόνο. Ο πρόεδρος του συλλόγου είναι ο Σοκράτης Βαρολογιάννης, είμαι εγώ. Και θα θέλαμε να ευχαριστήσουμε ακόμα πάρα πολύ την ομάδα εθελοντών μας. 30 εθελοντές μπόρεσαν σε ένα πολύ μικρό διάστημα, 30 ημερών, να συντονίσουν όλη την διεθνή αυτή εκδήλωση στη πόλη μας. Θα θέλαμε να τους αναφέρουμε ονομαστικά. Ευχαριστούμε πολύ τον Γιάννη Βουργίδη, που ήταν και στη τεχνική ομάδα, τη Ματίνα Τιβάγκου στη τεχνική ομάδα και τον Βασίλη Τσιούλο στη τεχνική ομάδα, που είχαν εξαιρετική εργασία. Θα θέλαμε να ευχαριστήσουμε τους συναδέλφους που βρίσκονται στο αμφιθέατρο, αλλά και τους συναδέλφους οι οποίοι εργάστηκαν και δεν μπόρεσαν να βρίσκονται λόγω των μέτρων περιορισμού του COVID στο αμφιθέατρό μας. Ειδικότερα ευχαριστούμε τον Νίκο Ντίνο, τον Γιώργο Γιακουμουγλίδη, τον Γιώργο Παύλου, τον Στράτο Κουτζανίδη, τον Κωνσταντίνο Στέρπη, τη Δήμητρα Νάτσικα, τον Λουκά Αλέξανδρο Παπαγεωργίου, τον Νάσο Νικολάου, τη Γεωργία Χρήσινα, την Παρασκευή Παλιούρα, την Κωνσταντίνα Κουμάνη, τη Θωμαΐς Παπαζόη, τον Κώστα Ρίκο, την Εύα Μπακάλη, τον Γιάννη Θιακούλη, τον Γιάννη Σιάνο, την Ειρήνη Κούλπα και τον Γιάννη Μίτσα. Σας ευχαριστούμε πάρα πολύ. Ελπίζουμε να απολαύσατε αυτό το διήμερο και να σας φάνηκε ως ένα γεγονός το οποίο μπορεί να προωθήσει την επιστήμη φυσικής. Ελπίζουμε να σας δούμε από κοντά τις επόμενους μήνες και το επόμενο χρόνο. Σας ευχαριστούμε πολύ.
Αν μου επιτρέπετε ένα λεπτό... εντάξει, οκ.
Ναι, κύριε Καρακασίδη. Κύριε Καρακασίδη, σας ευχαριστούμε επίσης. Επίσης, ευχαριστούμε το Τμήμα Φυσικής που ήταν...
Εγώ θα ήθελα να πω συγχαρητήρια στα παιδιά για τη διοργάνωση, τα παιδιά του Τμήματος Φυσικής. Συγχαρητήρια σε όλα τα παιδιά που συμμετείχαν από τα διάφορα τμήματα φυσικής και εύχομαι καλή επιτυχία, καλή πορεία και καλές αναζητήσεις, γιατί νομίζω η φυσική προσφέρει πολλές συγκινήσεις και πολλές και επαγγελματικές διεξόδους. Καλή συνέχεια εύχομαι, καλές γιορτές σε όλους και καλή συνέχεια στην προσπάθεια όλων σας εκ μέρους του τμήματος. Ευχαριστώ πολύ.
Ευχαριστούμε θερμά, ευχαριστούμε για την υποστήριξη που παρήχατε ως αντιπρόεδρος του Τμήματος Φυσικής. Ευχόμαστε τα καλύτερα σε όλους.